Welcome. This is Jen Rexford. I'm co-director with Nick Foster at Cornell with the Cornell Princeton Center for Network Programming. We're delighted to welcome you to our first Hangout on Air, beginning of a recurring series of technical talks on research in network programming. And for our first talk today, we'll have Mina Tambashi, who's a PhD student at Princeton, who's going to talk about her work on SNAP, Stateful Network-Wide Abstractions for Packet Processing. I just want to mention, if you're seeing the slides looking at all pixelated, you might want to change the resolution at which you're receiving the video. YouTube will let you adjust that, and we recommend setting that to 480 or higher to be able to see the slides with high quality. And with that, we'll go ahead and get started. And thanks, Mina. Take it away.
Thanks, Jen, for the introduction. Hi, I want to talk about SNAP, set of stateful abstractions for programming software-defined networks. But before we start, I want to say that we have a place for you to ask questions. Just use the URL and enter the event code, and you can post any questions you have during the talk, and we will get back to that at the end of the talk and try to answer as many as we can. So let's start with how traditional networks are managed and controlled. In traditional networks, each router or switch participates in a set of distributed protocols to exchange information about links, topology, paths, etc., with other routers and switches inside the network. Using this information, each router comes up with a set of forwarding rules to process packets and gets them to their destination. So this means that if the operator wants to implement a global network policy on top of this network, she has to think in terms of these distributed protocols. Basically, she has to configure each individual router or device such that when they exchange information with the rest of the network, they come up with the set of forwarding rules that the operator intends for that global network policy. And this gets harder and harder as the size of the network grows. And as a result, software-defined networking was proposed a few years ago. In software-defined networking, the operator can program the network from a logically centralized point called the controller. All the switches in the network connect to this controller, so the controller has a global view of the links, the topology, and the status of the network. The programmer or the operator can actually write a program that uses this global view to decide the rules for processing and forwarding packets, and can directly communicate these rules through the controller to the switches. Early SDN switch interfaces are actually pretty simple. For example, like OpenFlow. There are two ways for the programmer to communicate with the switches. First is to manipulate packet forwarding rules. These rules are match action rules, where they can actually match on a set of packet header fields, and then either modify or forward or drop the matched packet. They also have counters associated with them so that they can keep track of the number of packets or bytes that have matched the rules. And the programmer can actually pull these counters from the switches through the controller and incorporate that into the logic of her program that is controlling the network. The simplicity of these interfaces made them very widespread, but at the same time, it was problematic for implementing a set of network functions efficiently. And to make this point more clear, I want to go through an example of one of these network functions that is not efficient to implement with these early and simple switch interfaces. The example I want to talk about is detecting DNS reflection attacks. A DNS reflection attack happens when an attacker uses a botnet to send a large number of spoofed DNS requests to a set of open resolvers. The source IP address of these spoofed DNS requests is the IP address of the victim. So when these open resolvers want to send the responses back, they send them back to the victim, and the victim gets overwhelmed by the large volume of traffic that it receives. So the operator might want to actually detect that this attack is happening inside the network and prevent this traffic to get to the victim in the first place to overwhelm it. One way to detect DNS reflection attacks was proposed by a paper called Bohate in Usenix Security 2015. Based on what they have proposed, if you have a device that sits between the hosts that you want to protect and the rest of the world, what you can do is to log all the DNS requests that the hosts send out. When you receive DNS response back, you have to check whether you had a matching request word or not. If you had, this is most probably a legitimate DNS response, so you can just let it go. But if you didn't have a matching request for that, you want to keep a counter of the number of these unmatched DNS responses that you receive for each host. And you can keep track of this counter, and whenever it passes a threshold, there's most probably, the DNS reflection attack is going on, and you can mark the DNS traffic that is going towards that host as suspicious and let a mitigation engine take care of it or raise an alert. So now let's see how we can implement DNS reflection detection using, some early SDN switches like OpenFlow and a controller. So as I just mentioned, you need to keep track of some information across different packets, like the IDs of DNS requests that you have seen or the number of unmatched DNS responses that each host has received. And you cannot keep this information on the switches because you have no way of communicating with them that this is the information that you want to maintain. So you have to maintain this information on the controller. On the left, you can see a mapping that maps each host IP address to the IDs of DNS requests that it has sent. And on the right, you can see a mapping between IP addresses of the hosts and the number of unmatched DNS responses that they have received. So we keep all these mappings on the controller, and suppose that we want to protect the hosts that are inside the CS network, which is connected to our network on the right. So when we receive a DNS request from a host like H1 from the CS network, we have to send it to the controller so that we can record that we have received the DNS request with this ID from host H1. And then we send the packet back to get forwarded. When we receive a DNS response that is going to a host inside the CS network, we have to again send it to the controller to check whether we have a matching request for it or not. And in this case, we didn't because the ID was 200. So we're going to increment the number of unmatched DNS responses that this host has seen. And we send the packet back to get forwarded. So as you can see here, we have to send every DNS request and response packet that comes from the CS network or goes into the CS network to the controller. And this is simply not practical. So generally, you can see that from this example, that implementing network functions that require per packet stateful processing is really not feasible practically with these switches. And what I mean by per packet stateful processing is that you want to maintain some state across packets and then decide what you want to do with each packet based on this state. And we have actually looked through the literature and have found several examples of network functions for security, monitoring, or other purposes that actually need this kind of processing. So what can we do? How can we implement these network functions in a software-defined network? Well, the opportunity here is that we can use the local state on the data plane or on the switches themselves. Switches and routers have always had some local state. For example, a MAC learner switch keeps a mapping between MAC addresses and the ports that they're attached to, and it updates that on the fly when the packets are actually passing through the switch. The only thing that is that these local state used to be very customized to the specific type of packet processing that each device was doing and not exposed to the programmers to control. But recently, this has been changing. There have been a lot of proposals for switch interfaces that expose some of the local state on the data plane of switches to the operators to control. So they actually allow programmatic control over the state on the data plane. For example, they allow the operator to define an array of registers and control, how they change as the packets go through and how they affect packet processing. And examples of such interfaces is P4, POF, OpenState, and actually vendors have started to implement these interfaces. Vendors like Barefoot, Netronom, Xilinx, and also there has been research in the community of OpenVSwitch to try to support these interfaces like P4. So it looks like that our problem is already solved. We can just, put all of those mappings that we saw in the DNS reflection detection example on the switches and use the local switch, local state on the switches and avoid going to the controller. But there is another problem here, and that is the operator now faces a network of stateful switches, and she has to decide how to use their local state to implement her stateful network functions. Does she want to use one switch and to implement all the stateful network functions? Does she want to use a set of them, like distribute her network functions and the state across the network? And if yes, which switches does she want to use? How does she want to route packet through them so that all the packets see all the state value, all the state that they need? And this again is going to get really complicated and complex as the size of the network grows, or as you need, complex network policies. So this is the problem that we address here. We propose Snap, which is going to abstract all of these details and all of these difficult tasks from the programmer can just, so the snap actually provides the programmer with the abstraction of one big switch that is connecting the edges of the network and is keeping all the state of the network. So instead of thinking about programming a network of switches, she can just think about programming this one switch, and then the snap compiler is going to take care of distributing that program across all the switches in the network in an efficient way. So in this talk, I want to talk about first the language and the abstractions that it provides, and then about a compiler and how it manages to distribute the programs written in Snap across the network. Well, next I'll talk about the Snap language. A Snap program is just a packet processing function, a function that decides what to do with the packet. These functions can be stateless or stateful, and I will give examples of both shortly. A stateless packet processing function is a function that receives a packet as input and uses the values of fields inside the headers of that packet to output a set of packets. If this output set is empty, it means that a function has dropped the packet. If the function just wants to forward the packet as it is or modify a few fields inside its headers, this output set is going to contain one single packet. If the function wants to create multiple copies of the packet for multicast reasons or for mirroring reasons, then this output set will contain multiple packets. But the main point here is that the only thing that a function uses to decide what to output is just the fields inside the packet header, and it processes each packet independently of the other. A simple example of a stateless packet processing function is destination-based forwarding. In destination-based forwarding, what you do is that you just look at the destination IP address of the packet and forward the packet based on that. And this is how you can write it in Snap. It's very simple. It looks like a regular language. You have conditionals and if-then-else statements, which you can use to check the destination IP address and look which subnet it belongs to and forward the packet to the output connected to that subnet. And what I want to emphasize here is that this program is still written on top of the one big switch. So it doesn't talk about the path that a packet should take to get, for example, from ISV1 to the CS department. It just talks about which output out of the network the packet should take if it wants to go to the CS network. There have been several previous work that has provided programming languages for operators to express stateless packet processing functions like netcat, netcore, periodic, frenetic. And Snap is actually very similar to them in the stateless packet processing part. But what is new in Snap is that it also allows programmers to express stateful packet processing functions. In Snap, we had this one big stateful switch that could maintain state across different packets. So a Snap program, which is a stateful packet processing function, takes a packet and the current state as input and outputs a set of packets and the updated state. So it can actually decide what to do with the packet, both based on the packet fields and on the current state of the switch or program. An example that focuses on this stateful aspect of Snap programs is actually our DNS reflection detection. This is how you can write DNS reflection detection in Snap. And just to remind you, in DNS reflection detection, we need to maintain some information across different packets. And the way programmers can express the information that they want to maintain across packets is using state variables. State variables are what I have actually highlighted in red here. Each state variable is just a mapping from a set of fields to a set of values. For example, the sync state variable maps an IP address, which is supposed to be the host IP address, and an integer, which is the ID of DNS request, to a Boolean value that shows whether we have seen that request from that host or not. Unmatched is a mapping that maps IP addresses to an integer that shows the number of unmatched DNS responses that that IP address has received. And source is a mapping from IP addresses to a Boolean value that shows whether the DNS traffic towards that IP address has passed the threshold and is suspicious or not. So let's go through this program line by line and see how it is implementing our DNS reflection detection strategy. First, it checks whether the packet is coming from the CS network by looking at by matching on the source IP of the packet, and that is the DNS request by matching on the destination port of the packet. And if that's the case, it uses the seen state variable to record that it has seen a DNS request with the ID inside the packet from that host. If not, if the packet is a DNS response that is going to the CS department, we want to look at the seen state variable to see that if we have seen a request with that ID from the host that is the destination of this packet. And if not, we want to increment the unmatched state variable for that host. Next, we want to check whether the unmatched state variable has passed the threshold, and if yes, we want to mark the host as suspicious using a SOSP state variable. If the packet doesn't match any of the above conditions, it means that it's not of interest to our DNS reflection detection program, and we're just going to forward it as it is using the identity function. So now we have our DNS reflection detection, which monitors packets, and also our forwarding program that decides where the packet should head out. And we can put them together to create the whole policy of the network using what we call sequential composition. When two programs are sequentially composed, it means that the packets are going to be processed first by the first one and then with the second one. So in our example, the packets are first going to be processed by DNS reflection detection and then by forwarding. And this is just a simple example of composing programs together. What we envision Snap programs to be is actually a composition of several small programs, each responsible for certain tasks inside the network. And in fact, we have written all of those examples of simple stateful network functions in Snap and composed them together to run experiments, which I'm going to talk about them later in the talk. So now let's talk about the Snap compiler. The Snap compiler takes a high-level program as input, which is composed of different programs that can have state variables, for example, like our DNS reflection detection program. For all the reasons that we discussed before, we want to use the local state of the switches to maintain those state variables. So the compiler has to make two major decisions. First is the local state of which switch to use for maintaining each state variable. And even if that is decided, it also has to decide how to forward packets through the network and through these state variables. Remember that the Snap programs are specified on top of one big switch, so it's the compiler that has to decide which path the packets take through the network. And this is not trivial because an HTTP packet, for example, that is going to a host inside the EE department doesn't need any stateful processing. The ingress switch can just process it based on the forwarding program and forward it on the shortest path to its destination. A DNS response packet, though, that is going to a CS department, it needs all of those state variables for correctly be processed by our program. So the compiler has to make sure to choose an appropriate path for this packet so that it goes through all the switches that are maintaining the state variables that it needs. So in the first phase of the compiler, we do a program analysis to collect some information to help us in answering these questions about state placement and routing. More specifically, for each flow, we want to find out that first, does it need any stateful processing or not? And if it does, what are the state variables that it needs to be correctly processed based on our program? This is what we can figure out by a straightforward traversal of our programs, and I'm not going to go into the details of that in the interest of time. And second, we want to find out that if the flow actually needs some state variables for its processing, what is the order in which these state variables should be visited? And I'll just show you an example of why this order matters. Let's go back to our DNS reflection detection example and look at the parts that I've underlined. In this if-then-else statement, you can see that whether or not we increment the unmatched state variable depends on the value of the seen state variable. So there's a read-write dependency here that whether or not the write to unmatched happens depends on a read from seen. So if seen and unmatched are placed on two different switches, we want to make sure that a packet that needs both for their processing will first go to the switch that is maintaining the seen state variable so that it knows the value of seen. And next, it can go to the switch that is maintaining the unmatched state variable so that it knows whether or not unmatched should be incremented. So what we do to keep track of all of these dependencies is that we create a dependency graph that has state variables as its vertices, and then we traverse the program and keep track of all of these dependencies inside that graph. Well, now we have all the information that we need to decide state placement and routing in an optimal way. We have a mixed integer linear program that is an extension of the multi-commodity flow problem. And it receives the results from the program analysis phase and also the traffic metrics from the network, and decides optimizes state placement and routing to minimize congestion in the network. The constraints in this mixed integer linear program fall into two categories, one for routing and one for state placement, kind of corresponding to the two major questions that we wanted to answer. The routing constraints are very similar to the ones for multi-commodity flow. You want to have flow preservation. Basically, you want the amount of traffic that goes inside a switch be equal to the amount that is coming out. And when you assign paths to flows, you want to stay within link capacities. The state placement constraints are kind of similar to the information that we've gathered. We want each flow to go through all the state variables that it needs while it respects state dependencies. So with these constraints, our MIOP can decide state placement and routing. In the case of our DNS reflection detection example, because only the flows going to the CS department and coming out of the CS department need stateful processing, the MIOP finds out that the optimal place for placing all the state variables is the router adjacent to the CS network. But this doesn't necessarily need to be the case. Each state variable can be placed on any switch in the network as long as state dependencies are respected. So now we have actually answered our questions, but we're not done yet because we just decided which switch we want to use to maintain the state variables. But we still need to distribute the logic of our program across the network and tell each switch what to do to actually realize that high-level program. The problem that we're dealing with here is that on one end, we have this high-level snap program that is composed of many smaller programs. And on the other end, we have a network of switches that some of which are holding the state variables of these programs. And we want to distribute that high-level composed program across these switches. So to get from one end to the other end, we actually need an intermediate representation that is both easily composable so that we can compose all of these smaller parts together into one single structure, and also easily partitioned so that we can partition that structure across the network. For our intermediate representation, we decided to use what we call an extended forwarding decision diagram, or an XFDD. Our XFDDs are inspired by forwarding decision diagrams, or FDDs, that were introduced in a paper called The Fast Compiler for Netcat in 2015. FDDs were used for compiling Netcat programs that express stateless packet processing functions. So what we did was that we used them and augmented them to be able to express our stateful packet processing functions. An XFDD is a generalization of a binary decision diagram. It has some intermediate nodes that are tests on either header fields or on the state variables. And it has leaves that are sets of action sequences. You can see a simple example of an XFDD on the right. And as you can see, this is just a more structured way of representing packet processing functions, because you can just use this XFDD to decide what you want to do with each packet. Suppose that you get a packet. You can start from the root. It's a test that checks whether the destination IP address of the packet is equal to 10.0.0.1. It has two children, one of them connected with a solid line and the other connected with a dashed line. If the test passes, we want to continue through to the child that is the true child and is connected through the solid line. And if the test fails, we will continue to the false child that is connected through the dashed line. So in our example packet, suppose that the destination IP address is actually equal to 10.0.0.1. So we're going to continue over the solid line and get to the next test which tests whether the source IP address of the packet is equal to its destination IP address or not. And let's suppose that it's not, so it will continue over the dash line and get to a leaf node that tells us to drop the packet. I just want to mention that we have 3 types of tests in our XFTDs. The first 2 types just test on packet header fields. The first one checks whether the value of a field inside the packet is equal to a specific value. And the second one checks whether the value of 2 fields inside the packet header are equal. The third one is a state test that tests whether the value of a state variable at a specific index is index or key is equal to a specific value or not. And these last 2 types are what we have added to the original FTDs to actually make them support our stateful packet processing functions. And I'll encourage you to look at the paper for more details on why we needed to add these 2 types of tests. So what we do to actually construct these XFTDs for our Snap program is that we construct them for the smaller pieces of the program and then compose them together. For example, this is the XFTD for our DNS reflection detection example. And just to show you again that this is just another representation of our program, I'll just walk through one path in the program. So the program checks whether the source IP is inside CS network or not. And we have a corresponding test for that inside the XFTD. Next, the program checks whether the destination port is equal to 53 or not to check whether this is a DNS request or not. And we have a corresponding test for that inside the tree. And if both of these tests hold in the program, we want to change the value of the SYN state variable for that host and that DNS ID to true, and we have a corresponding action for that inside the tree. So we can create an XFTD for our forwarding example in a similar way, and then we have an algorithm to actually compose these trees together into a single XFTD for the whole policy of the network. Well, now we have the logic of our program in a very structured and organized way inside an XFTD. And what we want to do is to actually partition it and distribute it across the network. Our XFTDs are constructed in a way that they have 2 properties. First, the tests that only act on packet header fields, which are stateless, are gathered on the top of the tree. And the state tests and the actions that act on state are actually down the bottom of the tree. The second property is that the XFTD is constructed in a way that all the tests and actions on a specific state variable stick together inside the tree. So basically, we can partition our XFTD into subtrees, actually one stateless subtree and a couple of stateful subtrees, where each stateful subtree only acts on a single state variable. So when we have these partitions, we can assign the subtrees, the stateful subtrees, to the switches that host their state variable, and we put the stateless subtrees that are on top of the XFTD on the ingress switches. But let's see how these pieces of XFTD can work out together to process packets. Here on the right, we have part of our XFTD for the example program that we had. And the ingress switch that is connected to ISP1 contains the top part of this XFTD, which is the stateless part. So when a packet comes in, it can actually process the packet according to this XFTD along the green line up until node number 4, where there's a stateful test on the SYN state variable. Well, this ingress switch doesn't maintain the SYN state variable, so it cannot continue processing the packet. So it will mark the packet with the number 4, which is the number of the XFTD node where the processing the packet was stopped. And then it will send the packet to the node that actually contains that state variable. That router, edge router of the CS department, it contains all of the state variables. So it actually contains the partitions of the tree that have tests and actions on that state variable. So it can continue processing the packet up until the leaf node, the action node, and send the packet out to its destination. We have built a prototype of Snap to experiment with it. Our compiler is written in Python, and we use Gorby optimizer for solving our MILP problem. Once we distribute the XFTD, accept different parts of the XFTD to the switches in the network, we actually need to configure the switch so that it acts based on that XFTD that it was assigned to. The language that we chose for generating these configurations was NetASM. NetASM is kind of like an assembly for programmable assembly language for programming programmable data planes that was proposed by Shahbaz et al. In SOSR 2015. It has very flexible and broad instructions for expressing what you want your data plane to do, and it also comes with a software switch that can execute those instructions. So we choose NetASM to be able to express very clearly what are the properties that we need from a data plane to be a snap target. We evaluated our prototype compiler using 7 campus and ISP topologies, where each one had orders of hundreds of switches and links. We evaluated the compiler in 3 different scenarios. The first scenario was cold start, meaning that you want to run snap on your network for the first time. You have a snap program and have not been running snap before. And this is something that we think is not going to happen frequently, maybe every few weeks or every few months. The second scenario is policy change or program change, which means that you already have snap running on your network and you just want to change the program that is actually controlling your network. And this we think is going to happen with a frequency of days. The last scenario is when you have snap running on your network and the program is not changing, but a link fails or there is a dramatic change to the traffic matrix, which can happen every few minutes. And the reason we have distinguished these 3 scenarios is that each one of them fire different phases of the compiler. In cold start, well, you actually have to do everything. You have to analyze the program that you have received. You also have to create a model of your mixed integer linear program, like all the constraints for routing and state placement. And we actually found out that this phase is very time consuming, but fortunately, this is a one-time cost and it doesn't happen that frequently. And once you create all of those constraints, updating them actually doesn't take as long. Once you have your mixed integer linear program, you need to solve it to decide both state placement and routing. And then you want to distribute the XFTD and generate configurations. In a policy change, though, you need to still do the program analysis because your program has changed. You need to update the constraints about state placement because you have new state variables and possibly new state dependencies. But the constraints about routing don't need to change. And you want to resolve the mixed integer linear program to redecide state placement and routing. And then you want to distribute the XFTD and generate configurations. In the case of topology or traffic matrix change, your program that is running on the network stays the same. So you don't need to do any more program analysis. And also, you don't have new state or new state dependencies. So the state placement constraints can stay the same, but you might want to change routing constraints to account for the links that have failed or the traffic matrix that has changed. So given that, and given the fact that state placement is actually the expensive part to decide inside the mixed integer linear program, we decided that to react faster when topology or traffic matrix change happen, we can use the state placement that we were using as before and just redecide routing to route over link failures or switch failures. So we created a simpler version of that MILP that we're using to just redecide routing and not redecide state placement. And again, we have to generate configurations. So here are the results of running a compiler in these 3 different scenarios and compiling a program that is similar in complexity to the running example of DNS reflection detection. And as you can see, and as we actually expected, cold start takes the longest. It can take up to 6 minutes for our topologies. And most of the time is actually used to create the MILP model. But fortunately, this is just a one-time cost and doesn't happen that frequently. For a policy change, we can see that we can recompile the program in about 2.5 minutes for all of our networks and topologies. And when a topology or traffic metric change happen, we can actually recompile and recompile and redecide routing within a minute. So the takeaway, I think, from this experiment was that we can actually react faster to the scenarios that happen more frequently. And also, I think these numbers mean that Snap can be used with medium-sized or large-sized enterprise networks. We also ran other experiments to see how the compiler scales with the size of the network and number of state variables. And especially with the case that the compiler was scaling with the size, the curves for compilers scaled with the size of the network, we could see that the curves are close to exponential. And this is not surprising because the optimization problem that we're solving, that is jointly deciding state placement and routing, is NP-complete. But we still saw that for the networks that we tried, that were on the same order of those networks that I showed you earlier, we can still stay within a minute to react to topology and traffic metric changes, and that also still we can react faster to the events that happen more frequently. In terms of related work, I want to mention that Snap had several goals in mind. We wanted to have an abstraction for stateful packet processing, and we wanted it to be high level and network wide, like on top of the one big switch. And we also wanted to use the state on a data plane, and we also wanted to optimize placement and routing together because we thought that that's going to optimize them better. There are other works in the literature that have tried to solve some of these goals, but not all. I think the closest to Snap is actually Stateful Netcat. That is a language proposed in a paper called Event-Driven Programming from PLDI 2016. Stateful Netcat is very similar to Snap in the abstraction that they use for their state variables. And they also let users express programs on top of the one big switch. And they also use the state on the data plane. But there are some differences between the two languages and in the state that they use. Like the indexing is different, like we use packet header fields, they use integers. But I think the main difference is that we do joint placement and routing, but what they do in Stateful Netcat is that they put all the state at the edge and then do routing between them. There's also kinetic in stateful languages that also offers an abstraction of a stateful language, but it keeps all the state on the controller, so it doesn't satisfy the state on the data plane goal of Snap. There are other works that talk about programming languages, stateful programming languages for programming a single switch, and these works are highly complementary to Snap, and they can be used as a target for Snap. There are also works in mailbox literature for optimizing routing and placement over a network, and they try to decide placement and routing, but none of them actually do this decision in a joint manner, similar to what Snap does. So to summarize, I talked about Snap. The Snap language abstracts away all the details of the network from the programmer and allows the programmer to think about the network in terms of one big switch connecting the edges. And it also allows the programmer to compose several smaller programs together to create the overall policy of the network. Snap compiler takes care of all the hard work. It basically distributes the program across the network by first deciding where to place state variables and how to route packets, and then distributing the logic of the program over the network. And with that, I want to thank you for joining us in this talk, and we can go to questions to see.
Great, thanks, Mina. So we've had a few questions already that have come in, and of course the URL that's on the screen now, you can feel free to post your questions. I'll read them out and then give Mina a chance to answer them. So the first question is a question about failures and what happens when a link or a router fails, and in particular, how robust is the path chosen by the compiler to topological failures?
That's a very good question. So we don't choose multiple paths at compile time for every flow so that we can kind of switch between them when one of them fails. What we do is that we rerun the MIOP for now and redecide the route the routing and the paths when a link or a switch fails. If the switch that fails is maintaining some state, we actually need to redecide state placement too. But generally, what we tried to do was to make the MILP lighter so that we can actually react faster to failures. But definitely, it would be very interesting to see if you can kind of come up with multiple paths and it can kind of change between them at one time if one of them fails instead of rerunning the MILP.
Great. So another question concerning MILP actually is whether the model includes capacity constraints. And if so, if there's no feasible solution because the traffic exceeds the capacity, what does the system do?
Sure, that's a good question too. So there's some link capacities that we want to respect. And what we can do, so for now, we don't have that inside our objective, but you can definitely imagine that you can set an objective so that you can still send traffic over a link over its capacity, but then you will be exponentially penalized for that. So that you will anyway find a solution, but you'll try to find solutions that don't send much over the link capacity. In terms of, I mean, there are other capacity constraints too that we haven't implemented in our prototype, but are definitely interesting to look at. Which is how many state variables can one switch hold? Like in our example, for example, all the state variables were put on the router that was close to the CS department. So that then we only have 3 state variables. But what if we have like 50 or 100 and a switch, can just take care of a few state variables at line rate? So those are other capacity constraints that we haven't incorporated in our prototype, but they're definitely interesting to look at.
Great. So another question concerns the prototype, and it's a question about whether there are plans for a backend using the P4 language.
This is a great question. So in the beginning, we tried to have P4 as our backend, but there are some constraints for the current version of P4 to actually implement Snap fully and completely and correctly. And the reason is what P4 has is a set of registers that can be indexed by integer indexes. But our kind of state variables, they can be, for example, indexed by 2 IP addresses. So if you have a state variable that is indexed by, for example, source IP and destination IP, it means that you can have 2 to the power of, I don't know, 48 or something, 64 actually, 64 different combinations. And you can't allocate all of that inside the P4 program from scratch. So what you need is that you kind of need a dynamic table that keeps these mappings. And then you can update that as the packets go by. So you can implement that with a table inside P4 program, but P4 doesn't have support for adding an entry to a table inside the data plane itself. So if you want to add an entry to the table, you have to send a digest of the packet to the controller, and the controller should initialize, basically tell the switch to add an entry to that table, to that state table. And that means that you're giving up on your consistency because it can take a while till that rule is actually installed on that table, and that a few of the next packets may not see that update to state. So, and some programs are actually fine with that. Some of the security level functions are fine when whenever you detect an attack and start dropping packets, they really don't need you to start dropping packets, exactly the moment that you found out that the attack is happening. So yes, that would be very interesting to try to actually implement a less consistent version of Snap with P4.
Fantastic. And last question is just sort of general future work. What are sort of the longer term plans? What's next?
Well, there are many directions that I can think of that we have actually also discussed within our group. One of them is about what came up earlier about failures. So now we don't have any failure recovery mechanism inside the Snap prototype. So for example, if a switch that is maintaining a state variable fails, then we're going to lose that state. And we think that this is not kind of an inherent problem to Snap. Any distributed system, kind of needs a failure or a failure recovery mechanism for that. You need to keep backups for that state and everything. But we haven't thought about the best way to the best kind of distributed system mechanism to use for these kind of failures in Snap. And that's definitely one direction that I think is interesting. The other one is that if you want to scale Snap more, for example, to data centers or something, you definitely cannot pay the price of the MILP in some cases at least. So you might want to look at heuristics for doing joint state placement and routing. And the other thing is that we have some constraints in our programming model. For example, you can definitely, well, you cannot put the value of a state variable inside a packet and inside a packet header field. And the reason for that is that it's going to create some dependencies between state variables that we couldn't resolve in the beginning. So that's definitely another. And if you want to do something like NAT, you need that primitive that looks at a state variable. For example, in the case of NAT, which is kind of the set of free ports, and modify a packet header field based on that. So that is something else that we have been thinking about. And last but not least, many of these stateful applications actually need access to header fields that are above the network layer or at the application layer. And we think it's really interesting to think about something like a one big packet abstraction, where you can actually basically write stateful programs for packets like a full TCP packet or a full TCP stream, or like an HTTP packet, something like that. So that's another future work direction.
Great. Thanks so much. So thanks to everyone who joined in for our first Hangouts on Air for the Cornell Princeton Center for Network Programming. It's going to be a series of talks, and so we'd love to hear from those of you who attended today, who you are and what you thought of today's presentation, and also suggestions for future talks that we can offer in the upcoming months as part of this program. But for now, we're signing off. Thanks so much.
Thank you.